Welcome to the third lecture of basic electrical circuits. And in the last class, we looked at some basic elements, which were linear elements, and also independent voltage and current sources. We will continue from there in this class. Okay. Now, as this title says, it talks about elements in series and parallel and superposition and so on. So, like I had said, we'll also go by how fast we are going in each class and then what we did in the previous class and so on, so that we don't lose continuity. So, what we'll do is we will look at the elements in some more detail and then see what happens when we connect them in series and parallel. Okay. So, before I start, any questions about the previous class? Okay, there is a question from Vishal Goswami. What is the question? Hello? What is the question? Okay. Now what I'll do is I'll go to my notes and then start sharing that. Okay. The previous lecture we discussed independent sources. Independent sources, one of which was the independent voltage source. What it does is to maintain a given voltage V0 across its terminals. Okay. And it can carry any current. Okay. This what it means is the voltage source itself will not impose any restriction on the current. The restriction will come from whatever circuit it is connected to. That is the property of an independent voltage source. And the independent current source will maintain a current flow of given value through itself. Okay, and the voltage across that can be anything. Okay, so we looked at these, and these have IV characteristics. Which basically means the if I plot I versus V, which are straight lines. Not passing through the origin. Okay. Unless coincidentally the voltage source value or the current source value happens to be 0. Okay. Unless that happens, the straight lines are not passing through the origin, which means that these are not linear elements. Okay. Now, what is the definition of linearity? We said that linear elements obey superposition. In that sense, they will not obey superposition, because clearly the voltage across a voltage source will be equal to V0 no matter what current flows through it. So clearly, if you have two different values of current and then you add up the voltage source values, you will not get the resultant voltage when the sum of currents is passing through the voltage source. Okay. Similarly for the current source. In addition to this, we also looked at a certain number of linear elements, and this means that they obey superposition. Now, in case of electrical elements, the variables of interest are voltage and current. So, if V1 gives you a current I1, V2 gives you a current I2, then what superposition says is that alpha 1 V1 plus alpha 2 V2 will give you a current alpha 1 I1 plus alpha 2 I2. Okay. So, this is what is meant by superposition, and this has to be true if the element has to be linear, and also if this is true, the element is definitely linear. Now, which are the linear elements we looked at? The resistor R, whose voltage and current are related by a proportionality constant R, which is the resistance, and a capacitor C, whose voltage and current are related by the time derivative, and the C is the capacitance, and finally the inductor, whose voltage and current are related by a time derivative but in the opposite direction, and this L is the inductance. Okay. So, now all of these are linear elements. In case of the resistance, it's pretty obvious why it is linear. It's a proportional, the relationship is proportional, and that will give you linearity. And in case of capacitance and inductance, this time derivative is a linear operator, and hence these elements are also linear. Okay, which means that they will follow this principle. And it can also be in the other direction. That is, if I1 gives you V1 and I2 gives you V2, alpha 1 I1 plus alpha 2 I2 will give you alpha 1 V1 plus alpha 2 V2. Okay, so that is essentially what we discussed in the previous lecture. Now, what we'll do now is to consider some simple interconnections of these elements, okay, and see what they result in. Now, first, let's consider these elements in series and parallel. Okay. Now, what does it mean? We are, of course, talking about two-terminal elements. Now, if you have two elements, what is meant by a series connection? Series connection means that one element of one terminal is connected to one terminal of one of the elements is connected to a terminal of the other element, okay, and nothing else is connected to this, okay. So, this one of the terminals of this element number 1 is connected to one of the terminals of element number 2, and to that point nothing else is connected. Now, what this enforces by Kirchhoff's current law is that the same current is flowing through the two elements. Okay. So, a feature of series connection is that same current through the two elements. Okay. Is there a problem with viewing the notepad again? Okay, it looks like most people are able to see the notepad, so I'm going to continue. As I was saying, in series connection of two elements, you will have one terminal of one of the elements connected to one terminal of the other element with nothing else connected. And what it enforces is the same current through both elements. Okay, so that a feature of series connection is that the same current will flow through the two elements. Similarly, what happens in a parallel connection is that one terminal of the first element is connected to one terminal of the other element, and also the other terminals are connected together. Okay, basically one terminal of each element is connected to one terminal of the other element, and also the other terminals are connected together. And what it enforces is an equal voltage across the two elements. Okay, obviously by KVL, the voltage across this and the voltage across that have to be exactly the same. Okay, if you consider this connection between two elements as a loop, then the voltage will be enforced to be the same by Kirchhoff's voltage law. So for parallel connection, we will have same voltage across the two elements. Okay. So with this in mind, we can see what happens to each element as we connect them in series or parallel. Okay. So first, let's consider the independent voltage source. So let's say I have a voltage source of value V1 and a voltage source of value V2. And we connect them in series. Okay, that is, this node is the common node for the one terminal of each element. And what I want to find out is what does this entire thing look like from these two terminals. Okay. There is a question. What is the question? Hello? Okay. So what does it look like looking from these two terminals? I would like answers from the participants. When we connect these two voltage sources in series, the middle voltage is middle node is common to the two elements. So we have one terminal here and another terminal there. So if you look at it, the entire thing looks like a single two-terminal element. Okay. So what will it look like between these two terminals? So as a couple of people answered, this will the voltage across these two terminals would be V1 plus V2. Okay. So now this is so simple that I think all of you know the answer, but I will just show you how to do it formally. You can imagine some branch completing this loop and you apply KVL around this loop. The voltage drop across this in this direction plus voltage drop across this in the same consistent direction. Okay, and finally the voltage drop across this, and it has to be in the consistent direction, which is like that, has to be 0. Okay, so that means that in this polarity it will be minus V1 minus V2, or if I take the upper one and the upper one as plus and lower one as minus, it is V1 plus V2. Okay, so the bottom line is a series combination of voltage sources appears like a single voltage source of value equal to the sum of the voltage sources. Okay, and we can have more than two in series. So voltage sources in series equals sum of individual voltage sources. Okay, I think there is no confusion about this. Now the next thing is, what happens if you connect voltage sources in parallel? What will happen? That is, I connect this voltage source and that voltage source in parallel. Again, I would like answers from the participants. Okay, there were many answers and some of them said this connection is not possible, and that is correct. There are many ways to think about it. Here, first of all, the first voltage source is enforcing a voltage V1 between these two terminals, and this voltage source is trying to enforce a voltage V2 between these the same two terminals. Like, see, clearly there is a contradiction and that's not possible. Alternatively, you can think of this whole thing as a loop and write KVL around it, and the sum of voltages would be V1 minus V2, which cannot be 0 unless V1 happens to be equal to V2. Okay. So basically, to resolve this, we say that the parallel connection of voltage sources is not allowed. Okay. Now this gives you an inconsistent condition. Unless V1 equals V2. Okay, so unless V1 equals V2, you cannot make this correct connection. So you cannot connect voltage sources in parallel. So I hope that is clear. Yeah, there is a question from Ayush Dubey. Please go ahead.
Yes, sir. Sir?
Yes.
Hello?
Yes, please go ahead.
Sir, but practically we can connect two voltage sources in parallel. So what is the result in practical?
So the question is, in practice, if I take two voltage sources and connect them in parallel, what happens? Now, first of all, there are many ways to resolve this.
Yes, sir.
Whatever you get in practice will not be an ideal voltage source, right? It will not be able to hold a voltage of V1 regardless of what current is drawn from it. So what will happen is, if you connect two voltages, I mean, for instance, two batteries of unequal voltages in parallel, there will be some current flowing which will change the voltages of each battery. Okay, that is basically what happens. So the bottom line is there is no such thing as an ideal battery, ideal voltage source. Okay, so you can connect things in parallel. There will be some current that is flowing, and the voltage across each battery will be different from the ideal value. Okay, so that's what happens. Now I think many of you also know that if you have a real battery, that will be modeled not by just a voltage source, but a voltage source in series with a resistance. Okay, so you really cannot have these independent voltage sources which are ideal. This is a useful concept in circuit analysis and a useful approximation in many cases, but you really cannot do that. Okay, another way to think about it is that you have this net voltage of V1 minus V2 across some wires which have zero resistance. Okay, so that means that if you have V1 minus V2 which is not zero across zero resistance, the current through the zero resistance has to be infinite. Okay, so if you do have an infinite current, you can have some voltage drop. Now what it again really means in practice is that if you take two voltage sources or two power supplies of unequal voltages and connect them in parallel, a very large current will tend to flow through them and possibly damage the power supplies. Okay. Now there were also other answers like the maximum of the two voltages will appear. No, that is not correct. Okay, this connection is simply not allowed. Now we can look at current sources in a similar way. Let's say I have a current I1 and another current source of current I2 in parallel. Okay, that is both the terminals are common to the two elements. Now again this looks like some two terminal element here and there. The question is, what does it look like looking at those two terminals? Okay, answers please quickly. Okay, I think again the answer is pretty obvious. This will look like a current source of value I1 plus I2, and it's very easy to see. Basically, you want to find out what current is going there, and by Kirchhoff's law at this node, Kirchhoff's current law at this node, you see that whatever is going in here has to equal the current going in this plus the current going in that. Okay, so it forms a current source of value I1 plus I2. And you can have more than two current sources. So if you have multiple current sources in parallel, it is equivalent to single source with current equal to sum of individual currents. Okay. And we can quickly look at what happens if we have current sources in series. Okay. Now, just like with the voltage sources in parallel, you see that unless I1 happens to be exactly equal to I2, KCL at this node, at this middle node, is not valid. Okay, is not obeyed. If I1 is not equal to I2. Okay, so we say that series connection of current sources is not allowed. Okay, so unless I1 happens to be equal to I2, you cannot connect current sources in series. And you can see that it's complementary to what happens in a voltage source. You cannot connect voltage sources in parallel, you can connect them in series, and you cannot connect current sources in series, you can connect them in parallel. Okay. Next, let's look at resistors. In series and parallel. Okay. So if I look at a series connection of resistors, I have R1, R2, and the question is what it looks like from between these two terminals. Okay. Answers, please. Okay, again, I think the answer is known to a lot of people, and it is that it is equivalent to a single resistance of value R1 plus R2. Okay. Now, while this answer is known, it's also important to be able to derive this by yourselves. Again, this is a very trivial derivation, but for those of you who don't know, I will do it here and show it, because anything that you calculate, you should be able to do with confidence. Okay, you should be able to say why it is R1 plus R2, and from the basic circuit laws and the definition of resistance, we will be able to do that. Okay. Now, the easiest way to do that is, I want to find out what happens between these two terminals. Now, one general thing is that, let's say you are given a box with two terminals. We are talking about electrical circuits. Internally, there are some circuits, and two terminals are exposed to the outside, and you are asked to find out what is inside. Okay. The only thing you can do is to find the IV characteristic. You define I and V correctly, V with plus on top and I going into the upper terminal. Obviously, the same I will come out of the lower terminal because there is no net charge accumulation inside this element. So, you have to determine the IV characteristics, and that will tell you what this element is, what it behaves like, and so on. Okay. And to do that, you either apply a voltage source with a value V and determine I, or apply I and determine V. Okay. So, this is a systematic procedure that you will use repeatedly. Okay. So, in this course, you will later see, you will be asked like what is the equivalent of this circuit or that circuit. And the way to find out is by applying a voltage and determining the current, or applying a current and determining the voltage. So, now let us do that for our combination. In this case, what I will do is apply a current I will call it I test, because that is what I am using to test what is happening between these two terminals. And it is clear that this I test will flow through R1 as well as R2, because there is no other place for the current to go. Okay, we don't have nodes with more than 2 branches, so there is no other place for the current to go. So a current I test flows here. And if a current I test is flowing through R1, it will have a voltage I test times R1. Current I test is flowing through R2. It will have a voltage of I test times R2. Okay. So between these two terminals, I will have a voltage which is this plus that from KVL. Okay, because this voltage plus that voltage minus this voltage taken from bottom to top, that will be 0. Okay, so the voltage in this direction would be I test R1 plus R2. So the voltage drop is proportional to I test, and the proportionality constant is R1 plus R2. So if you know that if you have this resistance, the voltage across that will be I test R1 plus R2. Okay. Now this looks like a lot of work for deriving something so simple, but everything that you do, a lot of more complicated derivations will be things like this. Okay, it will be based on a systematic application of Kirchhoff's current law and Kirchhoff's voltage law, and also the relationship that governs each element. Okay, so that's why I showed this to you. Yes, please go ahead with the question. What is the question? Please go ahead with the question. Manoj Kumar. Okay. So a series combination of resistors will be equivalent to a single resistance whose value equals the sum of resistors. Okay. So you can have many resistors in series, R1, R2, R3, etc. Okay. When you have things in series, these intermediate nodes should not have any other connection. This point should have only two elements, R1 and R2, like here this has R2 and R3 and so on. If you have something else going off here, you cannot say that R1, R2 and R3 are in series. You also have to look at what is connected to this one. Okay. So in this case, this is equivalent to a single resistance, R1 plus R2 plus R3. Okay. Similarly, if you have resistances in parallel, we can determine what it looks like between these two terminals. Okay. And let's say I apply a voltage V and I try to find the current. Okay. So what I do is I will connect a voltage source, V equals V0, and find out the current. Now it's clear that this voltage V0 appears across R1 as well as across R2. So this current here would be V0 divided by R1. The current through R2 would be V0 divided by R2. And by applying KCL here, okay, at a node, we get the total current to be V0 by R1 plus V0 by R2. Okay. So the current is proportional to the voltage, which means that it's a resistance or a conductance, and the proportionality constant would be the conductance. Okay. Now if I write these in terms of conductances, the current here would be V0 times G1, where G1 is 1 over R1, and the current here is V0 times G2, where G2 is 1 over R2. Okay. So the total current can also be written as V0 times G1 plus G2. So this is equivalent to a single resistance whose conductance is G1 plus G2. When I write this, it means the conductance is G1 plus G2, or the resistance is 1 over G1 plus G2, which is 1 over 1 by R1 plus 1 by R2, which gives you the well-known formula for two resistors, R1 R2 by R1 plus R2. For more than two resistors, the formula will not look so simple, but it's much simpler to think of conductances when you think of resistances in parallel. Okay, the conductances will add up. And if you have more than two resistors in series, the resulting conductance will be the sum of individual conductances, and from that you can calculate the resistance. Okay. So let's say we had n resistances in parallel. Okay. So the total conductance would be the sum of conductances, where G1 is 1 by R1 and so on, and the total resistance would be the reciprocal of that. Okay. So this again is obtained by the simple experiment of connecting a voltage source and finding the total current. Okay. You can also apply a current source and find the voltage. That will give you the same answer, but it will be slightly more cumbersome, because when you have elements in parallel, the voltage is the same across the elements. It's easier to do it with a voltage source. And when you have elements in series, the currents are the same through the elements, so it's easier to apply a current source. Okay. Now, whether you apply a current source or a voltage source, you will get exactly the same answer, but I'm just pointing out that using the voltage source or current source may be convenient in some occasions. Okay. Any questions on what we have done so far? Please go ahead. Any questions? Okay, there were no questions, but somebody said if you have three resistances in parallel, the effective resistance would be R1, R2, R3 by R1 plus R2 plus R3. Now, I assume this person obtained this as an extension of R1, R2 by R1 plus R2, but as somebody already responded, this is not correct. Okay. In fact, this cannot be the formula for a resistance. If you look at the numerator, you have a product of three resistances. So the unit is ohm cube, and the bottom you have ohms. So this will have dimensions of ohms, units of ohm square. Okay, so this is not a resistance at all. So you can't extend it like this. What is true is that the resistance would be 1 by 1 over R1 plus 1 over R2 plus 1 over R3. It will be R1, R2, R3 divided by the pairwise product and the sum of those things, and it's a very cumbersome thing to write. So you may simply leave it as 1 by 1 over R1 plus 1 over R2 plus 1 over R3. So intuitively, it's easy to see that the conductances will sum up, and it's the counterpart of the series connection where the resistances will sum up. Okay. So these are the elements we have considered so far. Now next is let's say we take a capacitor and we can connect them in series and parallel. Okay. So let me first consider a parallel connection of capacitors. C1 and C2. So what will be the equivalent of this looking from these two terminals? I think many people answered this immediately. The answer is C1 plus C2. Okay. Now we'll see how that is. Again, if you use the procedure systematically, you will get the answer automatically. Okay, without any confusion. So again, I will choose to apply some voltage V of T. Okay. By the way, an independent voltage source means that the voltage value is independent of what current is flowing through it. The voltage value itself can be dependent on time. Okay. Now in the initial parts of this course, we will by and large look at voltages which are constant with time, but the voltage can be independent. Voltage can be dependent on time. An independent voltage source really means that the voltage value is independent of the current flowing through it. Okay. So here I have to apply a time varying voltage because if the voltage is constant, we know that no current can flow through the capacitor. Okay. If I do that, C1 has a voltage v of t across it, and C2 also has v of t across it. Okay. So the current through this would be C1 times time derivative of v of t, and the current here is C2 times time derivative of v of t. Okay. So the total current drawn from the voltage source is C1 plus C2 times time derivative of v of t. Okay. So obviously this is exactly equivalent to having a single capacitor of value C1 plus C2. Okay. The current going in here will be C1 plus C2 times time derivative of V. Okay. So a parallel connection of capacitors will give you an equivalent capacitance, which is the sum of all the parallel capacitors. Okay. Another way to think about it is, if you have multiple capacitors with a voltage V, then on this capacitor you will have a charge plus CV on the upper plate and plus C1 times V on the upper plate, minus C1 times V on the lower plate, and on the second one you have plus C2 times V on the upper plate and minus C2 times V on the lower plate. So if you associate this terminal with one plate and this terminal with the other plate, you will see that on the effective upper plate you have C1 plus C2 times V. Okay, and that tells you that the capacitance is C1 plus C2. Okay. Similarly, if we have capacitors in series, what will be the equivalent looking into these two terminals? What is it going to be? Okay, I am not going to show this. If at all any of you is not clear about it, you can derive it yourself. Again, I will say that you derive it while understanding every step of the procedure. You apply a current and measure the voltage. The result turns out to be a single capacitance C effective, and 1 over C effective will be 1 over C1 plus 1 over C2. Okay, or for two capacitors you can have this formula C1 C2 by C1 plus C2. Okay, so a parallel combination of capacitors, you get the sum of capacitance. A series combination of capacitors, you will get a formula similar to that of resistances in parallel. Okay, the reciprocal of the total capacitance will be equal to the sum of reciprocals of individual capacitances when you connect capacitors in series. Okay, and exactly the same thing can be done for inductors. I will not work it out. I will leave it as an exercise to you. If you have any difficulty, try to work it out again, following every step rigorously. If you have any difficulty, we can you can raise the question and we can discuss it in the one of the following lectures. Okay. So we have a series combination of inductors. What is this going to be equivalent to? As many answered correctly, this will be a single inductor of value L1 plus L2. And if you have two inductors L1 and L2 in parallel, okay, this will be equivalent to a single inductance L effective, and the reciprocal of L effective will be the sum of reciprocals of all these inductance values. Okay. So you can derive these things for yourself by applying a voltage or a current and finding the resulting current or voltage through the combination. When I say equivalent, there are these two terminals and these two terminals, and between them the electrical behavior is equivalent. That is, the IV relationship is equivalent. That is what is meant by equivalence. Okay. Any questions so far? Okay. Now we can look at certain extreme cases of element values. Now let me start with a voltage source